So it's actually afternoon where I am. So welcome to this morning's session. So for this morning, we will have two distinguished speakers. This session will be on quantum stochastic evolutions and dynamical semigroups. And without further ado, I would like to welcome our first speaker, Professor Luigi Accardi from University of Rome Tor Vergata, and who will talk about Stochastic Koopman program, quantum extension of classical evolution, and a unified approach to classical and quantum dynamical systems.
Thank you very much. I want to thank, first of all, the organizers who invited me to give a non-specialistic talk. So I will make essentially a survey of some old results. And the main idea will be the following. I will try in the first part to describe the stochastic version of the Koopman program and to show that it is strictly related to the quantum extension of the Koopman program. In the second part, I want to quickly describe how to outline, unfortunately there will not be so much time, outline a purely algebraic theory to the classical and quantum dynamical system. Finally, in the first part, I will discuss an interesting problem that arises comparing the classical and the quantum and the deterministic and the stochastic equations, and try to describe the structure of flows. Now, typically, you have a physical system is defined by states and observables. And there are a lot of mathematical models for states and for observable. But they share, among these many mathematical models, they share a common factor that observables are objects of a given category. And states are defined by some notion of duality of categories. Okay. So there are many examples that you all know, that you all know very well. They are examples of measurable spaces or measure space or topological space or manifolds. And in the algebraic domain, there's a hierarchy that starts with the general star algebra, ends with von Neumann algebra, and there is also the operator approach which goes through Hilbert space. Now, the advantage of the algebraic formulation is that it allows a unified approach to all these categories that I have mentioned before. For this reason, I will describe very briefly the Koopman argument and then try to generalize in a general framework. Here I will be very quick because I suppose that everybody knows very well. So the Koopman program started from a deterministic equation and with a given initial condition, and supposing that there exists uniqueness and there exists a unique solution, you can introduce the following map of RD into RD. If the solution exists for every initial state, this map will be a morphism of the category, and typically in the case of ordinary differential equation, the uniqueness of the solution implies the semigroup property of this family of maps of RD into RD. Now, example is the classical Hamiltonian system, where we have an additional property, namely that these maps of RD into RD also preserve the Liouville measure. So abstracting from from a Hamiltonian dynamical system, we arrive to the general notion of classical deterministic dynamical system in terms of a measure space, a family of one parameter group of invertible bimeasurable maps, which leave the measure mu quasi-invariant, that is equivalent in the Radon-Nikodym sense. Equivalent means that the Radon-Nikodym derivative of the evolved measure with respect to the initial one is strictly positive everywhere, so in particular invertible. Now, the Koopman program at Hilbert space level, so this is the Koopman program at the space level, at that measure level. At the Hilbert space level, you use the standard identification of L2 of S mu with the L2 of an absolutely continuous measure with respect to it. Remember that this P mu T is the Radon-Nikodym derivative of the evolved measure with respect to the initial measure. So if I divide, this is a standard isomorphism, and in this way you obtain a unitary one-parameter semigroup. In fact, it is a group because the maps are invertible. We suppose that the existence is a uniqueness theorem is true globally in time, in all T in R. Now, in the Stone, because of the Stone theorem, the semigroup is a generator which is self-adjoint, and we arrive that the original ordinary differential equation is equivalent to a Schrödinger type equation. You see, so in this sense, you, with the Koopman approach, you unify the classical and the quantum dynamical system at Hilbert space level. But there is another level in which this unification is even more important, and it is the algebraic level. Because if I identify a bounded measurable function with its multiplication operator by it, denoted MF, this is a standard multiplication operator, then you see that the standard, there is an action of the group on the algebra L infinity, which maps this algebra into itself. So the multiplication operator by F becomes the multiplication operator by F to the inverse dynamic applied to the same point. Now, you see, this is a first example of what we call a one-parameter automorphism group of the algebra L infinity. The infinitesimal form at algebraic level is a restriction essentially of the an equation of Heisenberg type. You see, this is an equation of Heisenberg type. The derivative of a certain quantity evolved in time, but now this quantity is an operator, is given in terms of the commutator. Now, this leads to the quantum extension of a classical deterministic system, because if you see in this evolution that you have here, you replace the multiplication operator by F by an arbitrary operator in, for example, in the algebra of bounded operators on the given Hilbert space, so you obtain you obtain here. So this leads, you obtain a evolution of the algebra of all bounded, or some case also unbounded operator. The infinitesimal generator again has the has now the full Heisenberg form, because this is the full Heisenberg evolution, because X is not necessarily a multiplication operator by a function. Now, the quantum extension of classical system are characterized, so this is an if and only if condition, by the fact that they leave an invariant for Neumann algebra, abelian for they leave invariant and abelian for Neumann algebra. If you start from a classical system, the abelian for Neumann algebra we have seen is L infinity, but bounded measurable function. So summing up, the Koopman program leads to the following equivalent: classical dynamical system, one parameter groups of operator, one parameter group of star automorphism of commutative algebra, extension to the quantum case, so non-commutative algebra. Okay. Now, everything that I said is extended to the case which the Hamiltonian system may, what I described before is the case of an Hamiltonian system so-called homogeneous in time. So the forces do not depend on time. But if the forces, Newtonian forces, depend on time, you have not a one-parameter evolution, but you have a two-parameter evolution. And we will discuss this because they are important for connection with probability theory. Now the stochastic extension. If instead of taking a deterministic map, for a deterministic map that to X associates the position of the state of the system at time t with initial state x0, now instead you take an initial state, you take a random variable with probability mu0, and therefore you have a stochastic process that you have that t associate the random variable, which depends, omega is a point of the algebraic, of the classical probability space. Okay, now the most interesting example we want to discuss is not the most general one, but it's very important, is the case when xt is a one-dimensional diffusion flow. So if xt is a one-dimensional diffusion flow, what does it mean, one-dimensional diffusion flow? Means that it is the solution of a stochastic differential, ordinary, classical stochastic differential equation when Wt is Brownian motion, x0t is a random variable independent on the Brownian, on the increments of the Brownian motion, which is called the white noise space. And we suppose also that x is in L2. The coefficients of the stochastic equation L and A are real valued functions, and we suppose they are regular enough, as we did before for the deterministic case, to guarantee the existence and uniqueness of the strong solution of this equation for every initial datum in L2. So, using Ito formula to have this equation, this equation is equivalent to an infinite family of equations that you obtain by putting, by taking the function ft, where f is a smooth function, as you see from the right-hand side, a little bit that C2 is sufficient, but I will not discuss technical condition in my talk. I will concentrate on the structure of these things, okay? So now, the important point is that now, why this, this formulation is the preliminary step for the algebraic formulation, because if you notice the map that to f belonging to an infinity of S mu of a classical probability space, associate f evaluated in xt is a star homomorphism. So in fact, I anticipate that what we will try to do is to formulate this equation in algebraic language. So in algebraic language, then you have this multiplication operator. But this multiplication operator now acts on the full space, which the space of the initial condition and the space of the increment of the stochastic processes. Okay. Now, the problem is we know that fxt we identify with the multiplication operator by f of xt. And now we want to do the same for the first derivative and the second derivative. This is done in a standard way, because you see, if you take the commutator of the derivation operator with the multiplication function, you get this essentially, the simple calculation shows that this is the multiplication operator by the derivative. So if you apply twice this argument, you see that the multiplication operator for the Laplacian is exactly the double commutator. Double commutator makes involves the partial derivative, which is not self-adjoint, but skew-adjoint. So if you multiply by 1 over I, you get a self-adjoint operator, which is called the momentum operator in quantum mechanics. And therefore, the first derivative becomes I commutator with momentum, and the second derivative becomes the double commutator. Everything is true in many dimensions. Now, the stochastic differential equation has this form. Remember, we start from an equation in which you have this term diffusion term, and stochastic term, because we have applied the Ito formula to the original stochastic equation for xt. Now, we want to put in algebraic language this, and we notice that if you have here, there is the term L, the first derivative of f. L times the first derivative of f, you can remember that the derivative of f is just the commutator with momentum times I. And then a simple calculation shows that this operator differs from the operator P, LP, L multiplied by P, just by a scalar, by multiplication by a function, which will commute with f. So the commutator will not change in the classical level. Of course, it will change when it acts on the quantum level. But so we obtain a nice self-adjoint operator. You see, we define the self-adjoint operator like this, and we obtain that this term of the stochastic equation, we can be written as a commutator. Now we do the same thing for the diffusion term, which is this term here, and we write again as using what we said before as a double commutator. Remember that P of A, now A is another multiplication operator by function that here will replace the operator L, okay? So after you do all these manipulations, you arrive to the algebraic, you arrive to show that the equation, the original stochastic differential equation, can be written in an algebraic form like this. D of ft is, you see, here you have the stochastic term, which is a Heisenberg type operator, because it is I times a commutator. Here you have again two Heisenberg type operators, which is the drift term, but then you have an additional drift term due to the double commutation, which is typically the dissipation term, okay? So the drift term, you see, that since the commutator is linear, you have PL here and P of this object here, so you put them together and define the new L operator, and you finally arrive to this form of the equation with a single stochastic term, and then you have the dissipation term, and you have a so-called Hamiltonian term. Now, using the notation that we had already introduced in the deterministic Koopman program, so this map that to f associate f of, as a function of xt is a staromorphism also in the stochastic case. And so we write an equation for jt. And the stochastic equation is that. You see, you have here the drift and the double commutator again. But now, jt, remember, is just multiplication by f of xt. So this is an algebraic formulation of the classical stochastic equation. Now, this immediately, as before, as we did for the deterministic Koopman program, we do for the stochastic, because we replace the multiplication by f by an arbitrary operator acting on L2 of R. And so we obtain this stochastic equation. Okay, so we extend the uniqueness and the existence theorem. Of course, this is true, and for this you need technical conditions on the various operators involved. But in many cases, you have such theorems. And the solution, what is? Is a classical operator process. You see, it is written as operator. It is written in a quantum language, but it's classical because the noise here is classical Brownian motion. Now, summing up what we did, we started with this classical stochastic equation. We proved that it is equivalent by Ito formula to this set of equation for varying f in a certain class of reasonably good functions. Then we introduced the map, which is a star homomorphism, which to f associates this f of t. And then we deduced an evolution, a stochastic differential equation for this family one parameter family of stochastic of star homomorphisms. Okay, so this is the unknown in this equation is JT, the family of homomorphisms. Okay, now last step is we extend to the quantum domain, replacing F by an arbitrary operator on L2 of the distribution, probability distribution of F. Okay, so, but this is important. One can prove that from using Ito formula that the solution of this equation is in fact, even in the quantum case, is an homomorphic. In the classical case, the F, we have the explicit formula. And so it's trivial to see that it is an homomorphic, a star homomorphic. But then when you have extended to the quantum case, even if the noise is classical, you have to prove that this equation has a solution, a one parameter family, which is an homomorphism, and this you do using Ito formula. But the Koopman program, if you remember well, was giving more than homomorphism, because it was giving an inner one parameter family of homomorphism. So in other words, in the Koopman case, we had a family, one parameter family of unitary operators, and the star homomorphism JT was expressed in terms of the unitary operators. Remember that this corresponds to the classical object of multiplication by function of the classical stochastic process. Okay, so we are here in a classical domain. Okay. Now, we ask ourselves, is it possible to do and to find and to prove that also in the stochastic case we can have this unitary operator? Okay. I say unitary because you can prove that if such an operator exists that has this property, that is for which this equality is satisfied, then necessarily the operator must be unitary. I will jump the proof for lack of time. However, so we have to prove that this one parameter family of homomorphism is in fact inner. And then we have realized completely the Koopman, the stochastic Koopman program. How do we do? Well, I just outlined the main idea. I don't do the calculation for lack of time, of course, but these are standard things, completely known. And so we postulate the exist, because if such a nu exists, it must be a functional of white noise, because JT is a functional of white noise, and U implements JT, which is a functional of white noise. So it is reasonable to expect that it is a function of white noise. So we postulate that also U satisfies a stochastic equation. But we know that U, and then we put our fundamental condition, that is that U must be equal to this. Now, we know the stochastic equation satisfied by this because we derived before using the stochastic Koopman program. But now we are supposing that also U satisfies a stochastic equation. So we derive a stochastic equation satisfied by this object U, T, M, F of X initial data, and U star T, using simply the Ito formula. We make the stochastic, the differential of the left-hand side, and using the Ito formula, we deduce an equation also for this part. And then we have the equation for this, and you equate the coefficients. So when we equate the coefficients, when we identify the coefficients of dW and dt in both equations that we have, you find what is called the stochastic Schrödinger equation. But it's classical stochastic because the noise is classical. You see, and the operator K, these operators, how they are related to the original. This is the Stochastic Koopman program, to show that the coefficients of the quantum form, of the algebraic form, let us say, we are still at algebraic level, can be expressed as a function of the coefficients of the original form of the equation, which is either deterministic or, in this case, stochastic. So the coefficients are given by this. I want to emphasize that when you have commutators involved, in the classical case, the coefficients exist, but they are largely non-unique. There are ambiguities. You can choose them in many ways, and this will depend, and they will give rise to different quantum extensions. Because when you have, you see, here you have one Hamiltonian term, one dissipative term, and the dissipation enters into W. This is the how to say, the prehistory of what in physics is called the fluctuation dissipation theory. That is the connection between dissipation and fluctuation. Now, you see the operators that enters in the algebraic equation are H Hamiltonian term, which is this, depend on L1. Remember that L1 depends on both drift and dissipation term in the ordinary, in the stochastic differential equation. And A is the dissipation term of the stochastic differential equation, and so it's not surprising that A derives K, which is the dissipative part. Okay, now we have achieved the full stochastic Koopman program. You see, however, note that while in the deterministic program we had an Hamiltonian equation, we had Heisenberg equation, but in the stochastic process, the operator K is self-adjoint, so K squared is positive, and there is minus I. So here we have I, a skew adjoint operator. Here you have a skew adjoint operator, which is good for Hamiltonian equations. But here you have a self-adjoint operator with negative sign, dissipation. So stochastic differential equation is not Hamiltonian, okay? And it must be, because if we want that the solution is unitary, this is a famous result of Hudson and Partasarati, okay? So what we conclude, that the requirement of unitarity of the solution of the stochastic equation is in contradiction with the Hamiltonian character of the equation. And this problem continues when we go to the quantum case that you will see in a moment, and we will see, well, this is another story. This problem took years to understand that, in fact, stochastic differential equation, both classical and quantum, are in fact white noise equations. So usual Hamiltonian equation, but with a white noise Hamiltonian. This came many years later from the theory of stochastic limit of quantum theory. Now there is the last step. Remember, last step of the Koopman program is to go from the algebraic formulation to the quantum formulation. But here, the quantum formulation is obtained not only promoting the operator of multiplication by F to an arbitrary operator, but also looking at the microscopic structure of the classical Brownian motion, which, as you know, from Hudson and Partasarati, is obtained as a sum of two quantum objects that I will not define here, because I suppose that people has a minimum of familiarity with quantum Brownian motion. But the important point is that the classical Brownian motion is the sum of two non-commuting Brownian motion, and the commutativity condition, the commutator of this Brownian motion is equal to the is equal exactly to dt. So this is the ancestor of the quantum Ito formula. Okay.
Excuse me, Luigi, you have 20 more minutes.
Okay, I will rush. So the quantum Ito formula, this is the famous Hudson-Pertas-Serratti quantum Ito formula, is given by this. You see, instead of dw equal dt, you have 4 objects, 4 possibility, because now you have B and B daga, and of this, only one is dt and the other one are 0. This is the so-called boson-Fock Ito table due to Hudson and Pertas-Serratti. Now we have, so to promote the classical, the equation now for UT, the most general equation is now to with arbitrary coefficient, which in the classical case, the B daga here there is a misprint. The second should be without a daga. The coefficient beta and gamma are the same for classical stochastic equation, but in quantum they are different. You compute the unitarity condition and you see that you find this equation for the stochastic version, for the quantum stochastic version of the Koopman operator. Okay, so beta now and H, beta and H, beta is arbitrary operator with under technical condition for existence, and H is arbitrary but Hermitian. So H is the Hamiltonian term. Now, all this algebraic, so now you see that by Koopman program, let me say the fundamental point, we have reduced every equation, either classical or quantum, to an equation for which can be either deterministic or stochastic for a certain flow. So you have the final result of the Koopman program was to deduce this equation in the 1-parameter family JT. Okay. Now, so it is convenient, since we have, as I said before, in the classical theory of dynamical system, there are a lot of categories that are used by different authors. In order to develop a unified language, we can speak of a category in which we have some object AS, which represent a prime S, which represent the state of the system, and the dual object AS is an algebra, typically is an algebra, or it can be a Hilbert space, and which represent the observable of the system at the same time. So in the Newtonian deterministic point of view, we have a forward evolution. I write evolution acting on the right on the states. So it brings the state at time S to a state at a future time t greater than S, and the backward evolution, which takes a state at time S, but brings back to a we take a state at time t, remember t is greater than S, and bring back to the state S. Okay, so this is the framework in which we are, a category with dual objects, states and observables, as we said before. And so we have the backward evolution and the forward, the forward evolution and the backward evolution. And in the deterministic, for reversible system, the backward evolution is simply the inverse of the forward evolution. Okay, so now we have a reversible deterministic system. Now, well, I will jump this part. This is not essential. Now I want to show some crucial point of this talk, namely the connection between unitary between dynamical evolutions and cocycles. So if you have a category and an object and with their dual, then we fix also a one parameter semigroup of typically put T equal to R. We take R and we consider it as a semigroup. Sometimes we restrict to R plus. Okay, we consider R as a semigroup, and we consider a one parameter semigroup which of T equal R, which each term of which has a left inverse, which we denote U0 minus T. Now, the fundamental connection between cocycles and semigroup is this. Take a unit, take a semigroup, one parameter semigroup. Ut is arbitrary, but U0T is a one parameter semigroup with a left inverse. And form this mathematical object. You see, you go forward with the UT evolution and backward with U0T evolution. Okay, and you form the one parameter family, JT. Now, this JT is no longer a semigroup because it's a product of two semigroups, but it satisfies a certain equation that I write here. In fact, it satisfies two identities that you can easily calculate by algebraic manipulation of the definition. So it satisfies, you see, first, instead of the semigroup equation, you have a kind of perturbed form because you have to sandwich S and T. When U0 is the identity, you find the semigroup equation. Okay. The important point that is essential for stochastic and deterministic equations is that the converse is true. So if a one parameter family satisfies this condition, then if I compose this family with U0, what I obtain is a one parameter semigroup. Okay. So there is a one-to-one correspondence between this special kind of product, backward and forward and backward, of semigroups and one parameter families which satisfy these identities. Now, this motivates the definition of one forward U0T cocycle. We say that if J, a certain one parameter family J plus T satisfies the equation that in the proposition, in the theorem, we have in the proposition 1, we have deduced starting from this equation. Now we take this equation, starting from this, we have deduced these two equalities. And now we take these two equalities as a definition of what it is a cocycle, a one cocycle for the U0T evolution, okay? So the theorem says that if I have a one cocycle and I compose, I have a perturbation of the semigroup, okay? Now I want to emphasize this point. You see, look at the left-hand side. Now suppose that we are in a category, say, of star algebras or even C-star algebra or von Neumann algebra, and all these maps are continuous. So it has a meaning to speak of strongly continuous maps. Okay, so if I have a product of two strongly continuous maps, in general, we will have that it is strongly continuous, and maybe some additional assumptions in the case of algebra is needed, but in general, this is true, okay? So the right-hand side is always strongly continuous. And it is very well known. So let us fix for the simplicity, the category of Hilbert space. So UT is a unit, so U0T is a one parameter, say, group acting on Hilbert space, and JT also acts on Hilbert space. We know that in Hilbert space, a strongly continuous the product of two strongly continuous semigroups is surely strongly continuous, especially if they are, well, in the case of they are both unitary. You imagine that they are both unitary. However, U0 is a semigroup, but this is only a cocycle, it's not a semigroup. So what can happen? What can happen? That since here you only need strong continuity, we know, and U0T is a unitary group, so a semigroup or group, you know that for semigroups or groups, strong continuity implies existence of a generator, differentiability. But for all groups, so also for the right-hand side. So you can have a situation in which JT is not smooth, is not differentiable, because strong continuity is sufficient. But this product is always strongly continuous, and therefore the right-hand side is differentiable. And in the case of unitary groups, it has a stone generator. See, this will be, I am anticipating this because I am afraid I will not be in time to arrive to the details of this point. So I want to formulate this as a theoretical possibility, namely that you have that U0 is a one parameter semigroup or group, so it is strongly continuous, it is a generator. This is strongly continuous, but not differentiable. So a priori, the left-hand side is not differentiable, but you know that the right-hand side is differentiable because it is a one parameter unitary group, and it is sufficient that it is measurable. But, but we know that it's even strongly continuous. So this is what the problem of the solution of this problem, which appeared in studying the concrete stochastic equation, took several years. It was formulated in a paper of mine in 1990, and the solution came out much later from stochastic limit again in 1990. Now, cocycles have also extremely important physical interpretation, because you see, this fact to bring forward with U in physics in the full Hamiltonian evolution, and U0 is a free Hamiltonian evolution. So to calculate the cocycle satisfies an equation which is called the Heisenberg equation in interaction representation. And the same is true if they are unitary operator. Okay. In classical physics or analysis, this is called the method of variation of constant. But there is another very important operator, interpretation of the cocycle, because the cocycle is interpreted also interpreted as so-called wave endomorphism. It's called as a wave endomorphism. Why? Let us see if it is inner, this cocycle. This cocycle is inner. So let us suppose that both groups are unitary, one parameter unitary group of automorphism, and they are inner. So the JT in this case has this form. And this operator that you define, you see defined here, that you defined here, is called the forward wave operator. You see, in the automorphism, you have for forward operator, U0 and UT are reversed, but we are now on observable, acting on observables. So that is why you see that you bring first act backward the free evolution and the forward the full evolution, full interacting evolution. The limit of the wave operator at time t is called the forward wave operator, and plays an important role in physics in definition of scattering operator. Now, I suppose the concept of filtration that is familiar in probability theory, you can extend to arbitrary categories. So you don't need to have sigma algebras. You can have algebras, Hilbert spaces, or star algebra, or von Neumann algebra. And this brings to the notion of adapted process. Well, we will say more general. An adapted map is a map that, when applied to an algebra localized in the past of T, leaves it invariant, provided that S is less than T. So this is the algebraic formulation of adapted maps. And then we have a notion of covariance for this evolution ut. Typically, we will use U0 T, which is given by translation, the algebra localized in I, you have I plus T. Now remember that I mentioned that I want to study the cocycles which are continuous but not differentiable. What is a condition slightly less than differentiable? Well, in probability theory is a very well-known condition that is called the forward differentiability. So in usual derivation, you take the limit of the increment, where epsilon can be negative or positive. In stochastic differentiation, you take the increment strictly positive, so in the future, and then you condition the increment on the past. And you take the limit not of the increment, but of the conditional expectation of the increment on the past. That is why it's called forward, because epsilon is always positive in this case. And we call it d plus xt. This is a generalization of the classical derivative, because you can prove that if x is differential, the process xt is differentiable in the usual sense, then the forward derivative coincides with the fundamental theorem of for stochastic calculus that says that if a process has a continuous forward derivative, so stochastic derivative, then the process xt is the integral of the derivative. But now, since I have an expectation value, this is not true absolutely, but up to an additive martingale. So what does it mean? What is a martingale, first of all? Remember that we have a projective family of conditional expectations, and the martingale is a process which is adapted, and such that for s less than t, the conditional expectation of mt over s, over the past of s, is ms. So this is a martingale. And this is true in any algebra. Remember, I am in a general category of algebra, so it works for classical and quantum. Conditional expectation is well defined also in quantum case. Okay, and now the fundamental theorem of quantum stochastic calculus can be formulated like
2 more minutes.
Okay, the fundamental theorem of quantum stochastic calculus can be formulated in this way. Suppose that xt is a continuous derivative. Then there exists a martingale such that the increment of x in the interval st is the integral of the stochastic derivative, the forward derivative, plus the increment of the martingale. And so you see that if we write this fundamental theorem in stochastic calculus in martingale form, we obtain, in differential form, we obtain the precursor of a stochastic differential equation. Now, the morale of all this is this: if we do all this procedure in the special case of a cocycle, you will find a stochastic differential equation of this form, where Bt is the forward derivative of the cocycle, if you start from the cocycle, and dm is a martingale. So this is true in the category of very general star algebras. Of course, you have to take care of the fact that typically Bt and dm will be unbounded operator, and so you will obtain the you have to do some technical condition for existence and uniqueness. What is the morale of all this? So what I did, I started from classical deterministic system. I arrived to show that it is associated to evolution. Covariant evolutions are cocycles. Cocycles are products of two semigroups. And then covariant evolution are cocycles, but non-covariant evolutions are, in probability theory, called multiplicative function. And then I did the converse operation. I started from a multiplicative function, and I found that necessarily it has an underlying dynamical system. This dynamical system may be deterministic when the derivative is a usual derivative. So the martingale term is 0. And it can be stochastic when the martingale term is non-zero. So you see that in some sense, the Koopman program is a converse. And I thank you for your attention. Thank you very much.
So thank you, Luigi, for a very interesting talk. So we have around 10 minutes for questions.
I have a question, maybe stupid question. When thinking about program, I think like computer program, like step 1, step 2, step 3, happiness. Can you please summarize what is a Koopman program in that sense? 1, 2, 3, happiness.
Allora, step 1, given a dynamical system in the classical state space, associate to it a one-parameter unitary group on a certain L2 space. So this is the first step, the Hilbert space step. Then there is the algebra step. Given this unitary group that I extended from the phase space group, produce associated automorphism group. Okay? Then there is the third step, which is once you have this automorphism, formulate the equation satisfied by this automorphism in such a way that this equation can be extended to a quantum domain in such a way that when restricted to the abelian algebra, L-infinity of S, the bounded measurable functions on the state space, you find back your evolution equation. Okay? So this is the quantum step. The quantum step involves evolution if you do it for ordinary evolutions, namely homogeneous in time, you get one-parameter groups. But if you do it for non-homogeneous dynamical system, you get two parameters evolutions. These two parameter evolutions are important. When you take the product of two semigroups, of which one has a left inverse, you obtain a notion of cocycle. And this is very important because cocycles are the natural perturbations of semigroups. So if all the philosophy of the quantum stochastic calculus is this: if I construct a cocycle with certain additional property, Markov cocycle, which is to be also localized, I have constructed a perturbation of a semigroup. Now, why this is important for physics? Because in physics, this is what you do. You start from a free Hamiltonian, which will give you a free evolution that typically you can solve. And then you want to find a perturbation. of it. Typically, the tools of operator theory allow to deal with rather regular perturbation. But the tools of stochastic equation allows to deal with an enormously wider field of perturbation, which are fundamental for physics and which are very singular. You can deal with the usual operator theory with enormous effort. But this enormous effort is useless because you have the tool of stochastic calculus that allows to replace this. So you see the program in steps is this. Start from classical, arrive to quantum. Then start from quantum, go back to classical.
And as a result of this program, we have several connections between important notions,
Yes.
plus some machinery to work with all this. Am I right?
Well, this unified picture came out from a huge quantity of concrete physical examples and mathematical examples. So this is a kind of conceptual synthesis, you see, that allows you to capture the structure. That is why I left all the technical points aside. I wanted you to have a unified picture, which is achievable in algebraic language. But all this came out, if you look at our book with Volovich and Liu, my book with Volovich and Liu, the stochastic limit of quantum theory, you will see that there are really a lot of application. Some of them are not known to the physicists. So they are not the mathematical physics that proves that a standard or something that the physicists already understood can be proved rigorously. There are several results that the physicists not yet understood. And this is, in my opinion, an important point of the true mathematical physics.
Thank you. You're welcome to send us our slides. We can publish them if you wish.
Surely I will send, yes.
So I think we still have time for one more quick question for Professor Accardi.
Hi, Luigi. Can I come in with a question? Maybe it's more of a comment. There's an interesting aspect here. So you've done things for basically the usual position and momentum operators. So that's on generally a Euclidean space, but you can generalize this to the case of a manifold, say a differential manifold. There your algebra functions is well understood. And you have this nice association of an operator with each vector field, this symmetric combination of the differential operator and the coefficients of the vector. I think in order to be self-adjoint, as I recall, the vector field on the manifold has to be a complete vector field. But it sets up quite a nice program then. You have basically the flows on the manifold, which you can describe then as really a stochastic system. And a lot of this seems to get overshadowed by the work of, for instance, Alan Kahn and non-commutative geometry, where they sort of take the Gelfand principle, where you have a nice manifold, you get the right conditions you want to algebraically extend this, then drop commutativity, and you're back down in the theory of manifolds again. It seems the philosophy here is more that you have something quantum stochastic. So there's a position, but there's also something conjugate to this. And it's sort of, yes, you can have something commutative in the center, but there's something else going on. And it's really just, once you focus on the commutative center, that's when you return to the classical world. So I just wondered, did you give any thought to, say, developing this theory? It's already generalized enough. within the context of, say, starting with differentiable manifolds as your object, your set of functions to quantize.
Yes, yes, yes. Partially, this has been done, and it leads to rather interesting object. Essentially, if you go, the natural environment is not a general manifold, but the natural environment is a general bundle, because typically in a manifold you restrict to the tangent bundle, but if you want to include the gauge theory for physics, you have to look at more general bundles. If you have listened to the talk of Boris Volkov, you can understand in what sense to include gauge theories, you have to have bundles. And this was done in a paper of 1982. I proposed a generalization of the quantum model in this direction. In that case, the unitary operator ut will be a two-parameter operator, which in fact depends on the curve, and it will be a version of the parallel transport. So there is something done, but there is not a systematic development, unfortunately.
Yeah. This is the paper with Annelish Mohari. Is that the one?
Right. That is where we discussed the general flows, but in 1982, I was discussing in what sense the standard Hilbert space model of quantum mechanics, if you extend it to a Hilbert bundle model, it is a very natural language to include gauge theory and some objects which are reduced to the standard Hilbert model when the holonomy group of you have a parallel transport is trivial. So there is a bridge between geometry and the kind of quantum model that you obtain.
Okay, thanks. That's very interesting.
Yeah.
All right, so let us thank Professor Accardi once again.